Look at a satellite view of Earth at night. You see a massive, interconnected web of power running continuously across entire continents. But for the engineers of the late 19th century, building this exact global system was thought to be physically impossible. If we go back to the 1880s, the nighttime glow of a city didn't come from electricity. It came from burning gas, coal, and whale oil. The electric light bulb had recently been invented, but the electricity needed to power it was effectively trapped. The dominant technology belonged to Thomas Edison. His system used direct current, or DC, a method where the electrical charge flows in a single, constant direction. The problem with DC was severe distance decay. Because the power dropped off so rapidly, dirty coal-fired power plants had to be built every few blocks just to keep the lights on in a single neighborhood. The engineers were trapped by an unavoidable physics problem. Pushing electricity at a low voltage was perfectly safe for home use, but it was too weak to travel down the street. Pushing it at a high voltage allowed the current to travel for miles, but it was lethal and would instantly destroy any connected light bulb. Without a way to safely step that high voltage down to a lower voltage mid-route, electrical power was stuck. It would remain a highly localized luxury for rich city neighborhoods, entirely incapable of becoming a global utility. George Westinghouse believed he had the solution. He threw his resources behind a highly controversial alternative called alternating current, or AC. Unlike DC, AC is a type of electrical flow that periodically reverses direction, which theoretically made it easier to change voltage levels on the fly. To prove this dangerous theory without Edison's spies watching, Westinghouse enlisted a brilliant, ailing engineer named William Stanley Jr. Stanley left the crowded industrial centers and retreated to the quiet, snowy hills of western Massachusetts, settling in the small town of Great Barrington. Stanley quietly took over an abandoned rubber factory on the edge of town. Inside, he began setting up a secret laboratory with a single, highly specific goal: to build a reliable mechanical system that could manipulate AC voltage over a long distance. This small-town experiment was an organized offensive. Stanley and Westinghouse were covertly developing a technology designed to completely dismantle Thomas Edison's electrical monopoly. This diagram shows a series circuit, an arrangement where electrical components are connected end-to-end in a single continuous path. AC technology was already being studied in Europe, but those early transformer designs relied on exactly this type of flawed linear wiring. Because current flowed directly from one transformer to the next, they were entirely dependent on each other. If a single shop owner turned off a lamp or changed their load, the entire town's electrical system would violently fluctuate or fail completely. Stanley solved the math by redesigning the physical connections. He developed the parallel connected transformer. Instead of forcing the electricity through a single path, he split the main power line into multiple independent branches. This parallel design perfectly stabilized the system. Every individual transformer could now draw power from the main line and safely step down the high voltage independently, without impacting the load of the neighbor next door. By decoupling the transformers from one another, Stanley had solved the final engineering bottleneck standing between a local experiment and a global power grid. On March 20, 1886, Stanley put the blueprint to the test. Step 1 was generation. Inside the rubber factory, a massive steam-powered generator roared to life, churning out 500 volts of highly dangerous alternating current. Step 2 was transmission. That 500-volt current surged out of the factory, traveling quickly and efficiently across 4,000 feet of overhead wire, strung straight through the trees toward the center of town. Step 3 was transformation. Waiting in the cold basements beneath the storefronts, Stanley's newly invented parallel boxes caught the high-voltage current and safely stepped it down to a manageable 100 volts. Step 4 was distribution. That final, safe voltage flowed out of the basements and into 23 independent businesses across Main Street, from the local barber shop to the post office. Stanley threw the main switch. Instantly, steady, flameless white light flooded the snowy storefronts. There was no smoke, no gas, and not a single flicker. On that night, Great Barrington successfully operated as a scale model. It became the first functioning, complete AC power distribution system on Earth. The success of this perfectly functioning prototype posed an immediate existential threat to Thomas Edison's business. In response, Edison launched a brutal public relations battle against AC technology, triggering what history calls the War of Currents. Westinghouse largely ignored Edison's smear campaigns. He took the blueprint verified in Great Barrington and immediately began scaling it up, mass-producing commercial AC systems and installing them in cities across America. By the 1890s, the technology achieved its ultimate test. Engineers constructed massive industrial penstocks into the rocky cliffs of Niagara Falls, using AC systems to capture the immense energy of the water. They sent that massive generation of power over miles of wire directly into the electrified street trams and businesses of Buffalo. Successfully lighting a distant city with water falling miles away proved that AC technology had definitively conquered geography. This diagram shows the 1886 map of the Great Barrington experiment dissolving into a modern grid schematic, operating on exactly the same logic. Every piece of electrical infrastructure built since relies on 4 unchangeable pillars: generation, transmission, transformation, and distribution. Whether you are looking at a sprawling urban hospital, a massive server farm, or the phone you are using to watch this video right now, your power access depends on this precise sequence. The sprawling, interconnected grid that powers our entire modern world is, in reality, just a scaled-up version of the exact same blueprint tested on one snowy Massachusetts street in 1886.
Thank you for watching. Please like and subscribe. It really helps us.